If we can build ships larger than skyscrapers, why do they still move so slowly? Not just a little slow, not slightly inefficient, but painfully, deliberately slow. A modern container ship can produce tens of thousands of horsepower, more power than hundreds of cars combined, more power than entire towns once used. Yet it crosses the ocean at a speed that barely beats a fast bicycle. At first glance, this feels like a failure, like something is wrong, like ship technology somehow fell behind while everything else moved forward. But ships are not slow because they are weak. They are slow because there is a hidden speed limit built directly into the physics of water itself. When we think about speed, our instinct is simple. More engine power means more speed. That logic works on land. It works even better in the air, where vehicles move through a very light fluid. But ships exist in a completely different environment. Water is not forgiving. Water is heavy. Water is dense. And water resists being moved far more aggressively than most people imagine. At low speeds, a ship mainly fights friction. Water sticks to the hull. It clings to the surface. It drags along every square meter of steel. This friction slowly steals energy. Engineers know how to manage this. They polish hulls. They use special coatings. They design smooth shapes to reduce drag. Friction is a known enemy, and it is manageable. But friction is not what truly limits ship speed. As a ship accelerates, another enemy appears. And this one is far more dangerous: waves. When a ship moves forward, it does not simply slide through the ocean. It forces water to move out of the way. That water must rise, it must compress. It must separate and reorganize. At the bow, water piles up and forms a wave. Along the sides of the hull, more waves appear. Behind the ship, a long wake stretches across the sea. These waves are not just water being displaced. They are energy. Energy taken directly from fuel. Every wave a ship creates represents energy that did not become forward motion. Fuel was burned, engines worked. But instead of pushing the ship ahead, that energy went into lifting and shaping the ocean. And here's the critical detail most people miss. The faster the ship tries to move, the worse this problem becomes. Wave-making resistance does not increase gently. It does not grow in a straight line. It increases dramatically. At first, adding speed feels reasonable. The ship moves faster. Fuel consumption rises, but not alarmingly. Then something changes. At a certain speed, the ship begins to interact with its own waves. The bow wave grows taller. The stern sinks deeper. The ship starts to climb the water it just created. Instead of moving forward efficiently, the ship begins pushing uphill. It is no longer just traveling. It is fighting its own wake. From this point on, speed becomes brutally expensive. You can add more power. You can burn more fuel. But the gains become painfully small. This is why many traditional hull designs have what engineers call a practical speed ceiling. You can exceed it, but it stops making sense. Doubling fuel might give you only a slight increase in speed. Tripling fuel might barely change anything at all. The ocean simply refuses to cooperate. So why not redesign ships to behave like speedboats? Why not let them skim across the surface instead of pushing through water? Because that solution only works for vehicles that are light and extremely powerful relative to their weight. Speedboats plane because they are small, because they are light, and because they are designed to sacrifice efficiency for speed. A cargo ship weighing hundreds of thousands of tons cannot do that. To make a ship like that plane, you would need absurd amounts of power. You would need massive structural reinforcement to handle the stress, and fuel consumption would explode to levels that make the ship economically useless. It might move faster, but it would fail at the one thing ships are built for: efficiency. And this brings us to the most misunderstood part of the story. Ships are not designed to be fast. They are designed to be efficient. A container ship cruising at around 20 knots can carry an entire city's worth of goods across an ocean. Food, fuel, electronics, raw materials. Pushing that same ship to 30 knots does not increase its cargo capacity. It does not make the ship more useful. It simply burns dramatically more fuel to fight the physics of water. This means the real speed limit of ships is not just physical. It is physical and economic at the same time. Even if engineers could squeeze a few extra knots out of a hull, the cost would be so high that operating the ship that way would not make sense. And reality proved this. When fuel prices increased and environmental regulations became stricter, shipping companies did something that seems counterintuitive. They slowed ships down on purpose. This practice is known as slow steaming. By reducing cruising speed, ships dramatically cut fuel consumption and emissions. Yes, voyages take longer, but the savings are enormous. Once operators understood where the real limit was, they stopped trying to fight it. Instead, they started designing around it. Hull shapes were optimized for lower speeds. Propellers were redesigned. Engines were tuned differently. Even global shipping schedules were adjusted. Everything began to reflect a simple truth. Beyond a certain point, speed is not progress. It is waste. This is why no revolutionary engine has ever made cargo ships dramatically faster. The bottleneck was never the engine. The bottleneck was always the water. So why can't ships go faster? Because water turns speed into resistance in a way air and land do not. Past a certain point, you are no longer traveling efficiently. You are spending fuel to lift the ocean, build waves, and fight forces that grow faster than power can overcome. Ships are not slow because they are outdated. They are not slow because engineers lack creativity. They are slow because they operate right at the edge where efficiency wins and waste begins. That edge is the critical limit, the point where faster stops meaning progress and starts meaning loss. Once you understand that, the ocean starts to look very different. What feels like a limitation is actually a carefully chosen balance between physics, engineering, and economics. Every ship you see crossing the sea is moving at a speed selected not by weakness, but by intelligence. So here's a question for you. If you could change just one thing to make ships faster without exploding fuel costs, would you change the hull shape, the propulsion system, or the way routes are planned? Leave your answer below. And if you want to understand how a strange bump hidden under the bow of many ships can save millions by manipulating waves, make sure you're subscribed.